Second.
Yeah, so welcome. I'm Dan McAdams, and I'll serve as MC a little bit today. Welcome to the Frontiers in Mechanical Engineering Sciences, a multi-university webinar series. So I want to welcome you on behalf of the organizing committee, if you will. It was an ad hoc organizing committee, but it was led by Devesh Ranjan and kind of pulled us together to see how this works. And before I dive in on some introductions, let me just put a advertisement for next week. So we're going to be a little bit more focused on mechanics and materials next week. Speakers are Juliana Albel and Ramathasan Thevaraman, and Jay and Reddy's going to serve as moderator. All right. So that'll be next week. So be sure to come back, same place, same time. And I'm going to introduce our speakers here, and I'm going to go from Jessica to Vinayak, and then I'll introduce Chris Wood and turn it over to him. So our second speaker is Jessica Menold. She's an assistant prof at Penn State. Checking her stuff. So she's been focusing on improving the effectiveness of new product development processes, integrating design thinking into engineering education, about understanding design cognition. Our second speaker today is Vinayak Krishnamurthy. He's an assistant professor at Texas A&M, and he's interested in a number of things: visualization, geometry, human-computer interaction, and visual elements of human-computer action. Our host and moderator today is Kristin L. Wood. He is the Senior Associate Design for Innovation, Senior Associate Dean for Design and Innovation and Engagement, which I think is a really great title. I'd like to have one like that myself. He's had a lot of different posts in the past. For many years, he was the founding head of Pillar and director at Singapore University Technology and Design program in Singapore. He's currently at UC Denver. Before Singapore, he was at the University of Texas, and he had the great pleasure of being my advisor back when I was getting a PhD. So that's his greatest accomplishment. It's not having me be a PhD student, but suffering through it. So with that, Chris, I'm going to turn it over to you, and I'm going to try to unshare my screen and turn my mute on.
Very good. Can you all hear me?
Yes.
Yes, Chris.
Good. And Devesh, my apologies. Some major technical problems in getting WebEx to work, and I sincerely apologize for coming late. But well, welcome everybody. It's an absolute honor to be part of the webinar series in mechanical engineering and sciences, represented by the illustrious universities that are partnering on this. And it's an absolute joy for the topic for today, which is on design, which is I know Dan McAdams' passion, my passion, and your two speakers' passion today. I was told by Devesh that we would, I'd have 5 minutes, so I'm not going to take a lot of time from the speakers. I want to give Jess and Professor Krishnamurthy time to really talk. So, but I will say, I hope you all get a chance to look at the ASME IDTC conference and the different sessions that were offered there this year, really representing the frontier of a lot of the research in the area. As well as I would encourage you to go look at ICED, the International Conference on Engineering Design and the Design Society. They have a great website that really, again, expresses the diversity, the breadth of topics, the basic research, all the way to application and making a difference in the world in our design field. So again, it's an absolute joy to be with you today, and I appreciate the kind introduction. With that, let's go ahead and move to our first speaker. And we're honored to have Professor Krishnamurthy from Texas A&M. He's an assistant professor. He'll be speaking on on solid geometry and other adventures in digital design ideation, and he's got some really cool papers in this area. Please. But before I head off, let me at least introduce. J. Mike Walker, Department of Mechanical Engineering at Texas A&M. He works at the intersection of 4 fields of research: geometric modeling, HCI, product design, and artificial intelligence. And he directs a wonderful lab called the Mixed Initiative Design Lab at Texas A&M. So please, let's join with Professor Krishnamurthy with his wonderful talk as he looks at the computational side along with digital design ideation.
Thanks very much, Professor Wood. I mean, it's actually an honor to be introduced by someone like you. One of the other days, I was talking to Dan that my exact statement was, "Is there anything that he has not done regarding you?" So if you think I do diverse, I think you passed the bar a long time ago. So thanks everyone for being here. A very big howdy from Texas A&M. I'm Vinayak Krishnamurthy, and I do a lot of different types of work, but overarchingly, I call myself a design researcher. And I think people in design would agree that it's a really fascinating area because you can actually end up doing anything you want, right? So my personal motivation as a design researcher actually comes from my teaching. So this would actually be my 5th year starting at Texas A&M in September, and I've taught this course in geometric modeling for mechanical design for about 4 years now. And every single time the students, so the course name is Geometric Modeling for Mechanical Design. When the students come in, they think it is SolidWorks for 3D printing, right? So there is a very fundamental difference that has, or rather, there's a phenomenon that has taken place because of the advancement of computational technology, where learning the tool has become the primary motivation rather than understanding the fundamental processes of design, right? So my research motivation actually comes from the fact that we need to come up with better ways to represent ideas, communicate ideas, visualize ideas, and so on and so forth, right? Every time a software changes, students are like, I don't know which button to press. So basically, they are spending 4.5 months learning how to press buttons on the computer, right? And we sort of, as educators, we also have to think about how to help them come out of that mode and then think about the design problem. So that's my motivation, which is stated by Sproul here, right? That we rarely invent a shape on a computer, right? We record it and we analyze it, right? So the grand challenge is for 3D modeling is to make simple modeling easy for more people and complex modeling accessible to far more people, right? So with that as a context, today I want to introduce, rather share some of the work that I've been doing for the last 2.5 years. And the term that I give to it is partitive solid geometry. Of course, this is one of my more geometric modeling oriented research, but I also do a lot of work on human perception and cognition in terms of how it can facilitate design. So if time permits, I'll tell 2 more stories which give a different perspective on how to support design ideation. Each of these could be a talk very easily, but we have a limited time, so I'll focus on partitive solid geometry together. The hope is that we'll get a little broader view of where we could take computer-supported design research in the future. Okay, so let's get to it. The origins of this idea, when I talk about it 2 years later, I can say whatever I want in terms of my motivation. But if you look at what we do in CAD right now, in almost all mechanical engineering CAD programs, the basic principle is based on this idea of constructive solid geometry, right? So you want to make a shape, and the way you make a shape is you represent it as a hierarchical composition. So you sketch something, you extrude it. You sketch something else, you extrude it. Maybe you subtract and add and create a union and so on, right? So the principle is bottom-up design, right? The philosophy is based on bottom-up design. So you'll see that hierarchy where you go all the way from the very bottom of the tree, and then you ultimately end up with a shape, right? And that composition is achieved through different Boolean operations as we define them in set theory. Now, this is typically what you will see in most of the engineering design systems. I'm not saying that there's no other way of doing geometric modeling. There's a whole bunch of, it's a very rich area, right? But typically in mechanical CAD, that's what happens, okay? And it's a very fine choice for forward design, meaning that if the designer has something in their mind that they want to express, right, as an intent in their product, they can use this paradigm and they can create some really wonderful products, okay? So it's excellent for design of products, no problem there. Now, I have been thinking about the generative design aspect of the workflow, right? So from there, at least just to set the stage for you, the basic idea for partitive solid geometry is to actually not look at the system from bottom up, but rather top down. So suppose you have a volume. The only question that I ask is, how can you partition that volume into some interesting pieces? Okay, why you need that partition and why interesting pieces, that we'll discuss a little later, right? So this is a more top-down approach, and the basic idea is to see whether we can represent these partitions in terms of spatial symmetries and in terms of medial geometries. Medial meaning skeletal geometries. Okay. And at least the purpose in my mind to think about this type of an idea for design is to see if we can bring more interactivity and a little more intuitiveness to generative design. So typically in generative design, and you can see Autodesk has been advertising it for the last 3 to 4 years now. Right? That the idea is that the designer provides some kind of a condition that if I apply this much amount of force, this is the amount of motion that should happen, and this should be the maximum mass that I need in my system. The computer may generate some interesting, cool geometries for you, and then you select and so on and so forth. To me, actually, that's one way of doing design, yes, but I think it takes the intentionality away. So I want to bring the intentionality back in the design of complex geometries, so that we can sort of bridge the forward and the inverse design workflows together. Okay. Just a disclaimer, I don't yet know how to do all this, right? Because I've only been working on this for 2.5 years now. And I think that there's a lot of collaboration needed to actually make this happen. Okay. Now for the truth, right? So the real reason why this entire thing came about was that I watch a lot of YouTube channels that talk about some cool math. Okay, so these are some of the channels. I'm hoping that many of you would also have watched some of these channels on YouTube and spent all Saturday afternoon doing random video watching, right? So one day in summer 2018, I stumbled upon this video. Okay, it's called "What is a Scutoid?" Like, okay, Scutoid sounds like a cool name. Let's watch the video. And so this gentleman right here described a very interesting shape that occurs in nature. Okay, so the real inspiration for partitive solid geometry came from this idea of geometry in nature. So there was a paper written in 2018 that talks about how cells form and how they shape up in animal skin cells. Okay, so if you look at animal skin cells, most of the times people will visualize them as prisms, right? So there's a whole bunch of polygonal prisms and you bring them together, and that's typically how people used to visualize. And when the skin is deforming, you change the prism to frustum. Now this group comes in and says that that's not how it happens. Actually, there's a completely new type of shape that occurs in nature that they called a scutoid, where you'll see that it's neither a prism nor a frustum nor a prismatoid. Okay, but actually something where there's a bifurcation that happens right in the middle of the shape. Okay, and when I looked at this, I asked myself, can I actually create this shape at will, right? So what would be the basic geometric principles to be able to create this shape, right? I like thinking first principles, so I seldom go and read the paper first, right? And then I realized that I'm not original because what I've thought is sort of already there. Okay, so as soon as I asked this question, I emailed my now good friend, collaborator, and also mentor, Professor Ackelman, in visualization. So he does a lot of interesting topological modeling. So I emailed him, and this is to all my junior faculty friends here. Never be afraid to email a senior faculty, because you never know what will come out of it, right? So we've had a fruitful partnership for the last 2.5 years now. Okay, so going back to that bifurcation, what that particular set of researchers found out is that if you look at the cell and you divide the cell into layers, okay, each layer is actually kind of a Voronoi diagram, and I'll describe that in some future slides. But essentially what happens is, when the cell is growing from basal to the apical layer, there is a topological shift that is happening at each layer. And you'll see that topological shift in this video. And this is exactly where that bifurcation happens, that the V shape happens. Okay. Not only that, notice that these are skin cells, which means that they have to fill space. Okay. So what we realized was that the space filling property and that nature of the shape are actually linked by a common principle, which you will actually see being applied a lot in nature. In fact, this is used very commonly even in geometric modeling, where we do triangle meshing and things like that using Delaunay triangulation. So the key idea is that of Voronoi partitioning. Suppose you have a plane. You have a bunch of points on the planes. We are going to call them sites. Okay. When you partition them according to this Voronoi scheme, what you will get is a bunch of cells such that each point in a given cell is closest to its own neighbor or to its own corresponding side. Okay. If you look at the edges, each point on the edge will be equally close to two of its neighboring sides, and so on and so forth for the vertices. So this has been used as a originally it came about, this idea came about I think in the 1800s by George Voronoi, who was looking at crystallography. But later on, people have found this to occur at several places in nature, including how leaves venate, and if you look at patterns in the sand, and the cracks and so on and so forth. Okay, so essentially you will see that this type of shape occurs very frequently in nature, in soap bubbles, for example. And the idea is that it is based on the principle of growth, right? So the sides are emanating circles. Wherever the circles meet, you're getting a partition of space. So it is by definition going to be space filling. Space filling meaning that if you put all the polygons together, you'll not have any voids. Okay, so that's the first principle for partitive solid geometry. We are partitioning a volumetric domain, and we want to be able to partition it in terms of space filling shapes. Space filling shapes in general have been, quite fascinating to the geometric modeling, or in fact, general geometry folk. So they've been cataloged by Goldberg very early, from 72 to 82. In fact, today we know that if you look at convex polyhedra, there are only 8 of these that if you just move around and assemble, you can fill space. None other actually are space filling, right? And only 5 of these polyhedra have regular faces. But when you see in nature, they have, you can find this in abundance. Okay, so let's go back to our image and look at what will happen if I move these sides. Okay, so let's run a video. So all these sides are moving together. Now you will notice that the topology of the cells of this partition is changing. And if you remember, this is the kind of stuff that was happening in scutoid also, right? So edges are collapsing, vertices are expanding at different locations according to the motion. Okay, so if we look at this movie as a spatial stack, right, this is what we are going to see. So each of these lines is basically a trajectory of those points, right, which is visualized across space, the third dimension, right? And let's just look at what happens to one of these shapes. So now you will see that those interesting bifurcations are going to start to occur once again. Not only that, if you put all these shapes together, they're still going to be space filling because every layer is a Voronoi partition. Okay, so that's principle 1, space filling shapes. The second principle for partitive solid geometry comes from spatial symmetries. Okay, so if you look at the previous video, the shapes are mildly interesting, but for us to be able to do something interesting with them, right, in terms of engineering design or product design, we want to be able to design complex structures that are A, repeatable, and B, fill space. We know how to fill space, but we don't know how to make them repeatable. Okay, and the logic is very simple. If you look at several applications in architecture, in mechanics, even in art, for example, you will see that many of these symmetric shapes make appearance, right? So we want to have a systematic methodology so that we can understand how these shapes can be made, how they can be designed, and how they can be controlled for certain types of behaviors that we want in mechanical systems, right? So that's the second principle and the motivation for the second principle. Okay, so let's start with simplest form of symmetries, 2-dimensional symmetries. So there are only 17 of these. These are called wallpaper groups or wallpaper symmetries. Basically, if you want to imagine, if anyone has ever played with a kaleidoscope, these are the types of symmetries that you might end up seeing. Okay, so if we go back to our basic line structure and try to see how we can make it more interesting, what we can do is we can make the top and bottom points such that they are symmetrically placed on the 2 planes, and then we can interpolate between them. So once we do that, we see that you start getting some interesting type of a shape, right? Which has that property, by the way, the bifurcation property, but it also is space filling, and it is a unique shape. That is, it's a unique tile that you can just replicate in space and fill the entire space. Okay, so now we are starting to cook something. Okay, so if we go back to our very first observation, right? We started with this bifurcation. We figured out, okay, something happens because of the topology change in Voronoi. Okay, what specifically happens is that the vertex valency is changing to 4. So one edge is collapsing and then it is expanding in the other direction, which means that at that very moment, the valency of the vertex is 4. Why are we interested in this? Because not only do we want to create repeatable shapes, we also want to, remember I said, can I will this bifurcation to happen, right? So I want to find out what is the rule for this bifurcation to happen. Okay, so if we assume a rectangular arrangement of points on a plane and assume that it's an infinite plane and an infinite grid, right? You can appreciate that the Voronoi partition of this grid is going to be looking something like this. Now notice that each of the vertex of each of the cells has a valency of 4, which means that if we were to actually design our shape such that we always ensure that the bifurcation happens, all we need to do is that put this as a slice somewhere in between. Okay, so this is the first paper we wrote on the concept of as an example of partitive solid geometry that we call Delaunay lofts. Okay, the idea is that you start with a rectangular grid in the center, okay, and you create lines up and down such that it follows some wallpaper symmetries on the top and the bottom planes. As long as you have those symmetries, you will have the uniformity, or at least some level of uniqueness in the tiles that you can fill the space. Okay, so this is one example where you'll see a pentagonal tiling that is being interpolated from the bottom to the top. Okay, and once you know this, you can then create a whole different varieties of shapes. All we are doing here is changing the point structure on the top and the bottom planes, and based on the wallpaper symmetries, we get a whole bunch of interesting varieties of shapes. Okay, so far so good. We saw two different principles: space filling based on Voronoi partitioning, and symmetries to give us a unique shape that can tile itself. Okay, so these are some 3D printed examples. Now the third principle is looking at the sites themselves. Okay, so far when we have looked at the shape, we have looked at a slice, and each slice is a bunch of points, and we are generating a Voronoi partition using those points as sites. But do we really need to do this? Do we need to do it layer by layer? What if we directly take these lines, suppose we call them control lines, and we do a Voronoi partitioning directly on the basis of these lines? So this is the third and final principle that defines the entire idea of partitive solid geometry. So the first is Voronoi partitioning guarantees space filling shapes. The second is symmetry allows for periodicity and many times uniformity. And the third is higher dimensional sites open up a very rich design space for creating controlled partitions of volumes. Remember that we want to be able to intentionally design things. So we want to be able to control where and how the partitions happen. Okay, and just to give you a sense of the different types of things we can do just using these three principles, these are different types of symmetries. So for example, we have 2.5 dimensional symmetries, which is like cylindrical and woven. By 2.5 dimensional, I mean you're thinking about shells. Okay, then we have 3-dimensional symmetries like the sphere, for example. Okay, so you can partition any domain that you want if you know what your site looks like and how it is arranged in space, which is the symmetry aspect. Okay, so let's look at one application of where this kind of a geometric modeling scheme could be applied. Okay, and here I'm going to present an example on topologically interlocking structures. So basic idea for topological interlocking is that if we have a collection of elements or geometric elements or shapes, right, such that we apply a peripheral force, like forces on the sides. So suppose I put a rubber band on on this assembly of weird ellipsoidal shapes. Okay, just on the basis of their geometry and the mutual arrangement of the shapes, these elements are going to be locked in space. That's the idea of topological interlocking. Okay, there is a counter idea of geometric interlocking that I will not go into, but at this point of time we'll focus on topological interlocking. And this is generally a very interesting idea to many folks in materials design, in mechanical, in architecture, and so on. From a mechanical engineering perspective, these types of shapes basically exemplify the philosophy of toughening by fragmentation. Cautionary disclaimer, I'm not a mechanics person, so if you want to talk about this more, please feel free to give me some new knowledge about this. Okay, so essentially these have been explored in architecture for a long time. These are called Abel's flat vaults and then Trouché's vaults, and people have used these to create architectural shapes. Okay, and in the recent times people have tried to do the same with computational tools also. And then you have applications in mechanics where it allows for more impact resistance, and most of these shapes are basically based on Abel's original idea. So we were interested in seeing if we could use something like topological interlocking and see how we can explore this notion of partitive solid geometry. So if you look at Abel's original vault, right, this is the basic unit that you will see. It's essentially a truncated tetrahedron, right, and which is truncated along the edges. So each of these pieces, essentially, if you put them, extend them, they'll become a tetrahedron. So if you look at this shape, you will see that there is a very nice pattern on the top and the bottom surfaces of this shape assembly that I'm showing you. Okay, and it's actually based on the idea of weaving, fabric weaving. This is something that we had not expected, by the way. Okay, we saw this as a more visual analogy, and then we figured out that actually this is it's possible to have a correlation between the two concepts. Okay, so weaving basically gave us the idea that we can apply the notion of weaving as a means to create symmetries. So this is one example that I'm showing you. I'll show you the process of how to go from the weaves to the tiles themselves. Okay, so on the left hand side you see that if we induce two different weave symmetries on the top and the bottom, and we arrange our Voronoi sides accordingly, then we end up getting shapes that actually are going to be topologically interlocking. The assumption here is that they will not move under a peripheral force, assuming that there is no friction. So even if there is no friction, purely geometrically, they are not going to move up and down. Okay, so the idea behind doing this computation is that suppose you have points in the plane, you do Voronoi partitioning, this is what we get, right? We get these sets. Instead of Voronoi partitioning of points, suppose we have lines that are arranged according to the weave symmetries, we get a partition like this. Now, notice that these curves, these are not arbitrary curves. These are actually analytic curves. In fact, they are specifically parabola. Okay, so essentially what we do is that we apply these two symmetries on two planes, top and bottom planes. We construct our Voronoi sides. So this is one example of side geometry. And based on this, we populate the entire fundamental domain, which is our volume. And we do Voronoi partitioning, and we get a partition such as this. Okay, so we can explore a whole different bunch of side geometries. We can also explore a whole different bunch of weave symmetries, and we get a really, really rich variety of shapes, all of which are topologically interlocking. Okay, so we did some physical evaluation, numerical evaluation rather, not a physical evaluation per se. And we sort of compared it with a monolithic block, and we see that there is a very clear relationship between the geometry that is coming from the symmetry and the way in which stresses are distributed across these tiles. So I believe that if we explore this idea further, this can be utilized for design of different types of structures for different types of applications. Okay, so the big picture for partitive solid geometry is that it affords us a very rich design space, wherein you can choose from a variety of shape domains, like what kind of domain you want to partition, different types of spatial arrangements going all the way from 2D, 2.5D to 3D, different types of designs of Voronoi sides, and different types of distance functions. Now, let's remember that when we are talking about Voronoi diagrams, we are basically talking about distance fields, right? So it's essentially the idea is to create spaces that are closest to their corresponding sites. So different distance functions, different metrics can result in different types of partitions. Okay. So in terms of as a representation for a shape, we now have a more medially based shape representation that can allow for the creation of a lot of interesting complex geometries. And because the sites themselves are visual in nature, my hope is that we'll be able to construct better human-computer interaction systems where people will be able to intuitively design these types of shapes. Remember, I'm a larger proponent of forward design. Apologies to whoever is more fascinated by inverse design, right? And in terms of modeling workflows, we can use them for different types of applications such as architecture, metamaterials, education, and so on, right? So essentially,
So Vinayak, I'm going to just dive in here real quick. We're at the 25-minute mark, a couple more minutes and clean it up.
Sure, yeah.
Thanks, Chris.
These are the last couple of slides that I'll present. So, I said digital design ideation, right? So if you look at generative design right now, it's sort of like a black box. The user doesn't know what and why the computer is giving you the shapes that it is, right? So the idea is that if we can make some effort to make that process a little more intuitive, in the sense that people understand the relationship between the geometry and behavior, then we might be able to create better design systems, okay? And the whole purpose of introducing this new geometric modeling paradigm for me was to actually look at that aspect of interactivity, which is sort of what I'm planning to do over the next few years, okay? So this is an open invitation to all people who do anything in metamaterials, thermofluids, or acoustics to talk to me and see if we can do some interesting applications for partitive solid geometry. My favorite one is, education. It's a joy to watch my son play with some of these 3D printed shapes that I bring home. So I think that this could be a very interesting future direction as well. So I would like to end this talk. Well, unfortunately, I couldn't share all my adventures, but I'd like to end this talk with a list of all my collaborators and my mentors and also my students. They really do the work. I just give talks, right? So if I missed somebody, apologies from my side. With that, I'd like to stop and wait for questions. Thank you.
Great. Vinayak, thank you so much. Virtual applause from all of the webinar attendees. Thank you. What we'll do is we will hold questions, Vinayak, until the end, and we'll have them for both you and Jess, if you don't mind. So we'll move on. And Vinayak, thanks so much for the wonderful presentation on your approaches, new approaches in solid geometry for design and design ideation.
Thank you.
So participants and audience, let's move on to our second of the two talks in design today. We're honored to have Professor Menold from Penn State University. Let me introduce her title of her talk and a little bit about Jess. So the title of the talk is Opening the Black Box Towards a Deeper Understanding of Design Cognition. Really wonderful to see the diversity of talks that we have for this webinar today. Professor Menold's talk, our background is that she is currently an assistant professor in the School of Engineering Design and the Department of Mechanical Engineering at Penn State. She's director of the Technology and Human Research in Engineering Design Lab and conducts research at the intersection of engineering design, manufacturing, and new product development. Dr. Menold is also the inaugural associate director for their outreach and inclusion program at Penn State for their makerspaces. So I very much look forward to Professor Menold's talk, and Jess, I'll hand it off to you.
Thank you so much, Chris. I really appreciate it. So hi, everyone. As Chris said, my name is Jessica Menold, and I am an assistant professor in engineering design and mechanical engineering at Penn State. I'm also the director of Thread Lab, and today I'm going to be speaking to you about my work exploring the cognitive economics of design by starting to unravel the relationships between designers and prototypes. First, though, I do want to just take a second to really introduce my lab, which is the Technology and Human Research and Engineering Design Lab. as Chris mentioned. But the work and the findings I'm going to share today is really thanks to the amazing graduate students and undergraduate researchers that we have working with us in Thread. We're a fantastic, huge family, and I'm so honored to be able to work with these students every single day. And again, much of the work that you're going to hear about that I will be presenting on today is very much in large part thanks to their efforts. So in Thread Lab, we really focus on exploring and investigating the processes involved in the design of engineered products and systems. And our goal is to study the humans engaged in design and problem solving and the intelligent products and systems that they design, including some of the products and systems that we design, so that we can develop methods to really support effective and efficient design practice. And today I'm going to be discussing some of our work looking at the people responsible for design. So we got to hear some of the really interesting talk in the first session from, kind of new intelligent systems that are being created. And today I'm going to talk a little bit about how do we kind of come up with some of those intelligent automated systems by looking at the humans responsible for the design and the cognitive strategies behind some of these innovative products. And design, I want to kind of first start with just a background, right? Design represents a really unique form of problem solving, as design problems are often characterized by ambiguity and unknowns. And so the cognitive effort really required to formulate design problems, to generate solutions, to leverage design strategies, or even to navigate the social dynamics of design teams, especially for an engineer, can be quite high. And so the problem-solving processes involved in developing a design solution are incredibly complex. And that's really where my work comes in and what I'm fascinated by. So my work really focuses on modeling these cognitive strategies that designers employ, because if we can start to codify these strategies and start to identify which strategies are more or less effective, we might eventually be able to create some sort of a predictive model that could be used to guide the selection of design methods and the timing of these methods in the design process to really increase the overall efficiency and effectiveness of design teams with respect to innovative output. And so ultimately, my work is developing automated and intelligent tools, not to remove the human from the design process, but really to complement and amplify humans' creative abilities. And I'm going to be talking about a very particular type of design activity today, and that is prototyping. And prototyping is a really fundamental part of design, and it has a number of benefits that are documented in literature throughout the design process. And so we know that prototypes serve as important tools for generating new concepts. They can help to validate designers' ideas, inform design decision-making. They also act as aids in developing kind of designer knowledge, and they help designers to identify and articulate unknowns. And they also help designers to communicate insights and communicate key features to stakeholders and to critical stakeholders that can help build buy-in and trust in really risky concepts. And kind of one of my favorite quotes that I'll share with you is from a very famous prototyper, James Dyson. We all know him from the Dyson vacuums. And he's quoted as saying, from cardboard and duct tape to ABS polycarbonate, it took 5,127 prototypes and 15 years to get it right. And even then, there was more work to be done. And I love this quote because I feel like it really highlights the importance of prototyping to his innovation process. But also it highlights something that a lesser known fact about James Dyson, right? So he was quite wealthy before he invented the vacuum. And we know him as being famous for this, but in reality, right, for most design teams, for most designers, for most industries, spending 15 years on a prototype is simply too long of a design time, right? And taking the financial capital to make 5,000 prototypes is simply infeasible. And so it's really critical that we start to understand the cognitive processes designers are engaged in during prototyping, so that we ultimately might be able to increase the efficiency and effectiveness and reduce the overall costs of prototyping efforts. And prior research has kind of focused almost exclusively on the outcomes of prototyping. So, and some of the kind of costs that are associated with them, but mainly the financial costs of prototyping tasks. And again, the goal of these past researching efforts is to identify strategies that can reduce the overall cost of prototyping in particular. But this really fails to acknowledge that the main purpose of prototyping, the reason we build prototypes as engineers, is to identify unknowns and to answer questions and really advance the design solution. We call this the coevolution of the problem and solution space. And so the discovery of design knowledge and the interpretation and use of that design knowledge is absolutely critical and almost defines the success of prototyping efforts and ultimately the design project. And so the crux of what I'm going to talk to you about today is that it's really critical that designers have the appropriate cognitive resources needed to meet the demands of a cognitive prototyping task. And so I'm going to kind of dive into this a little bit more, but cognitive effort, first of all, kind of need to start with this definition. And this is defined as the fraction of limited attentional resources that are momentarily allocated to a problem-solving process. And we know from prior work that the cognitive effort required to accommodate certain design tasks and complex design activities can actually act as a barrier to the advancement of the design process as well as the design solution itself. And this is because when the cognitive effort demanded by a design task exceeds the cognitive capabilities of the designer for an extended period of time, the designer might feel overloaded and the likelihood of burnout and stress increases significantly. And they'll be unable to process any new design information that emerges from that design task. Conversely, when the cognitive effort demanded by a task does not meet a minimum threshold, it's not complex, it's not challenging enough, the designer could become disengaged, they will become likely unproductive and unmotivated. And so you can really think about this very similar to the dynamics of a marketplace, which is characterized by this equilibrium or lack thereof between supply and demand. So the balance between the cognitive demands of a design task and the cognitive supply of a designer is really critical. And this is, again, because approximately 50% of product development costs are incurred during prototyping and testing efforts. So my work specifically focuses on prototyping tasks and the cognitive efficiency and effectiveness of the designer because they are inextricably tied to the financial costs of prototyping. And so as designers uncover information during prototyping efforts, the design solution advances. But again, if the cognitive demands of prototyping exceed the cognitive supply of the designer is really going to be incapable of processing that novel design information. And so to start to get at this, my lab, some of our work has really focused on studying the people behind design, the cognitive strategies that they employ. And today I'm going to talk to you about a series of controlled studies and in situ studies that are ongoing in our lab. And we've been conducting, these studies, mixed methods in situ studies aimed at really unraveling and characterizing the links between prototyping tasks and designer cognitive state. And in particular, we've studied the narratives that designers use to rationalize and justify design decisions in order to identify what factors may be influencing designer behavior during prototyping tasks. And I'm going to talk about one study in particular that was really interesting that we conducted with novice designers. And so in this study, we worked with about 46 novice designers, and we asked these designers to build a tower. And the design problem itself represented a multi-objective challenge and really forced designers to make trade-offs and to make design decisions throughout their prototyping tasks. And our goal was to understand what factors may be driving design decisions during prototyping tasks and evaluate if designers were able to correctly perceive the influence or the level of influence of these factors. And what we found was that designers tended to reframe and contextualize their design solution as a success post-mortem, so even though it failed. Essentially, what we saw here was kind of that the cart was leading the horse, so to speak. We found that designers were reframing the problem itself, often creating imaginary constraints or proposing new performance objectives to really justify their design decisions during prototyping. So for example, we had one individual state that his design was a perfectly designed tower because it used as little glue as possible. However, that was not one of the performance objectives that we gave this student, right? It was about weight, strength of the tower, aesthetics, and so glue had very little to do with it. However, they reframed the problem itself to make it look like they're, and to kind of lessen the severity of their failure. We also saw that designers had this tendency to blame external factors on failures, even in cases where it was abundantly clear that these external factors had little to do with their own design decisions. So we recorded audio and video of these design experiments, and we're conducting some natural language processing on some of the audio in some cases, finding some really interesting phenomenon. In one case, we had a designer state that I could not gain access to some of the equipment, particularly hot glue guns, and thus I had to pivot my design and choose to create a tower with self-locking pieces. However, as you can see in my photo, there were lots of hot glue guns, lots of equipment readily available. And if you look back at this particular designer's ideation sheets, there was evidence of self-locking parts and for their tower in those ideation sheets. And so it's interesting that they were reframing their failure as and kind of blaming these external factors. We also had some designers kind of had a tendency to distance themselves from their own decisions just by using a passive voice. So they would make claims like, well, the measurements were made incorrectly or the lines were not drawn correctly, and so I had to pivot, right? When in reality, they themselves were drawing the lines, they themselves were making the measurements. And so what we kind of pulled out from all of this was that when designers were faced with failure, they exhibited narratives that really could be linked with a weak locus of control. And locus of control is a psychological concept that refers to how strongly people believe they have control over their own situations, their own experiences, and their lived narratives. So we hypothesized that the stress of this particular prototyping task may have exaggerated certain designers' perceptions of control and the role of external factors in their overall success or failure. We also found evidence to suggest that certain cognitive biases, such as self-serving bias, or the sunk cost effect, which is a fairly well-known cognitive bias in prototyping, may not only have been affecting their design decisions, but might have been affecting the narratives that designers construct after the design process is complete. This was really interesting. And so we also saw through some of these studies, right, that prototyping technology, right, the manufacturing tools we use, might also be shifting and changing design decisions. And so in this previous study, however, right, we were only able to gather design data post-design task. And we wanted to, myself and my graduate students wanted to kind of dive back into this phenomenon and understand how tools and other variables might be changing the design behavior of designers across time. And how are these variables really shifting the trajectory of the design itself? And this was a particularly timely study because, as we all know, additive manufacturing has become commonplace, especially in some of our undergraduate engineering education environments. And so what I saw as I was teaching was that students had this tendency to drift towards additive manufacturing. And I realized that this new technology, this digital technology, was kind of fundamentally changing the way the designers were prototyping because they were integrating more digital prototyping earlier in the design process. So in order to really understand how some of these design tools and other variables might be interacting with design cognition and design decisions over time, we conducted an in-situ study with higher level engineers. So we had about 79 design teams engaged in the design and development of autonomous robots. And we collected data over the course of 16 weeks, and we collected everything from photos of prototypes, CAD models, surveys of designer cognitive state, engineering requirements. And these were all collected from teams just, again, to start to unravel more holistically how these variables are interacting and shifting design trajectories over time. And what we found was incredibly fascinating. So first of all, what we're seeing based on our findings is that designers might be overly influenced by the prototyping tools available to them. And particularly, we're saying that we're seeing something that we're calling manufacturing fixation. So design teams tended to make design decisions based on the constraints of the prototyping or manufacturing technology available to them, rather than based on the constraints of the design problem itself or in pursuit of a design solution that met the design requirements or the user needs. And so as an example, consider kind of a well-known heuristic for designing a part for additive manufacturing. And this is the use of self-supporting overhangs, right? When you're designing something to be 3D printed, you want to avoid generally large overhangs to reduce the amount of support material. And what we saw was that students who were using additive manufacturing had a tendency to stick with additive manufacturing, meaning they would never transition to another prototyping tool, but they would also redesign their solutions to incorporate some of these heuristics. And these were based purely on the constraints of the additive manufacturing machine. And often these design decisions had little to do with the driving requirements or specifications of the design itself. And so at first, yes, it might seem like they're just changing some surface level to make it a faster print. But ultimately, we saw this waterfall change happening where they were changing a small geometry and then they were changing a larger part of the functionality. And so kind of in other words, designers were adapting their designs to meet the needs of the manufacturing technology not to meet the needs of the user or to satisfy engineering specifications. And this is really problematic because ultimately this could lead to necessary redesign very far down the road when it's much more costly. And so I'm going to kind of switch gears a little bit and talk about some preliminary data that I'm excited about and some preliminary studies that we're conducting. And so more recently, we've been looking at kind of the physiological signatures of designers and how that could help us to kind of characterize and understand cognitive state during prototyping a little bit better. And so what we found is in preliminary findings that they're kind of suggesting that designers, of course, might be cognitively overloaded during very complex prototyping tasks, and that we can use their physiological signatures, so their electrodermal response, heart rate, to predict or to kind of in real time understand their cognitive state and understand when they might be experiencing high levels of cognitive load. And again, this is really critical because we want to understand this connection between this cognitive overload and cognitive state, and how designers ultimately are interpreting and processing emergent design knowledge. And is this leading to irrational decisions or suboptimal design output? So I kind of threw a lot of our studies at you, and so I just really want to summarize, what does all of this mean? What is my work kind of leading to? And what we're finding is that, first of all, individual designer cognitive state could be a predictor of larger firm level outcomes. And this is, again, really interesting because in some other studies that I didn't have time to present on today, we're working with startups, predominantly technology-based startups. What we're seeing is that there are these linkages between larger level financial outcomes at the firm level and state at the individual level. And so it's really important that we begin to understand how individual designer decisions and complexity of tasks might be linked to larger firm level outcomes. We also found, that designers have this tendency to reframe design problem, and this is particularly true of novice designers. So really, the designers were shifting the goalposts and kind of changing the original design problem so that their prototype was a success. But again, this is not the purpose of prototyping. It's not to build a fully functional, perfect model that has no flaws. The purpose of prototyping is to discover fundamental knowledge about the problem and solution space and really evolve both spaces at once. And so this was highly problematic that we saw in kind of this novice designer behavior. And we also saw, the choice in design or prototyping tools, how this is starting to really shift, and it might be a small shift at first, but ultimately leading to larger level shifts, shifting the design trajectory. And it's really critical that we understand how digital prototyping tools might be shifting the very nature of prototyping tasks, because it certainly has effects on long-term design outcomes. So the last kind of thing that I want to leave you with, and what a lot of my research is pointing to, is that prototyping is a cognitively and a financially expensive task, and that these two variables are very tightly linked. And so we're just starting to kind of peel apart some of these links. You can almost think about it like a Gordian knot, right? And so we're trying to untangle this and really understand how prototyping, the cognitive costs and the financial costs might really be linked. And so by developing this fundamental understanding, my goal is to really create the methods and tools to support practice. And I want to leave some time for questions. So if you're interested in any of our other work in cybersecurity or additive manufacturing, please check out some of our work on thread.group, or you can follow us on Twitter. And just a shout out to some of our sponsors for supporting this research. But thank you very much, everyone.
Great. Thank you, Jess. Again, a virtual applause, or we'll at least hear some sound of applause for that wonderful presentation by Professor Menold. Great. Well, thank you. It is question and answer time. So Jess, because you just finished and you got to a second, if you don't mind, if we start off with a question for you.
Sure.
This is actually from your counterpart today, Vinayak. And he asked the question of, what steps can design educators take to mitigate some of the issues you mentioned regarding novice behavior, especially as we are all trying to integrate prototyping fab technology within our courses. And I might just do also a quick addition to that, and also managing this cognitive economic for our students.
Yeah, I think, some things that I have found successful. So I run a lot of both graduate and undergraduate level prototyping courses where the whole course is just us prototyping all the time. And what I found is that, obviously engaging in a lot of reflective practice is one way to make designers a little bit aware to cognitive biases as well as to their own kind of issues or problems or stumbling blocks. And so in my class, I do something that's called ungrading, where they actually try to like really reflect and kind of grade themselves and justify those grades. And so I found that has been just helpful more broadly. And then additionally, with respect to prototyping technology, I'm certainly, a nerd when it comes to that stuff, right? I have a 3D printer, right behind me in my downstairs, and I absolutely love all the novel prototyping technologies that come out. But what I found is really important, and what I do a lot at the Learning Factory in my role as the director there as of a diversity inclusion, is really teaching not only the kind of cool, fancy new stuff, but getting back to basics and saying, well, if you wanted to create a tube, right, you certainly shouldn't be 3D printing that, right? That's a 24-hour print. Let's throw it on the lathe and we can make it in 10 minutes, right? So really trying to help students to connect to some of these old school manufacturing technologies that are certainly not outdated and very much still have a place. Getting back to sketching sometimes and kind of trying to find that balance between both sides.
Love it. Thank you. And really it's about, giving approaches to help. There's so many dimensionalities of prototyping, and especially design prototyping, and really creating that balance. Jess, thank you. Vinayak, a question for you. This originates from Dan McAdams, but also when I was jotting my questions down for you both, I had a similar one. But it relates to self-similarity and multiple scale. Have you considered using self-similarity types approaches, looking at your geometry, and as you generate those at different scales like you would fractals? Mm-hmm. For example, to look at behaviors in engineering concepts like flow, stress, and others.
Right. So that's a great question. So because we have so far been, focused on the fundamental principle development, we haven't yet actually looked at things like that, right? Self-similarity and things. But having said that, if you see one of the few shapes that I would have shown, essentially, if you were to consider a simple one complex, like a tree, for example, you can actually use those structures in a very natural way to, induce self-similarity in the three-dimensional shapes that you get as well, right? So I think it would be certainly interesting to look at some of those shapes too. That's a great question.
Thank you. And if you don't mind, I'll also follow up, and I'll send some questions to both you and Jess after that. But let me go back to Jess. Appreciate the answer. This is from Ying Kwang. Ying Kwang asked Jess, thanks for your interesting presentation, and it very much was. What I wonder is how we choose the types of prototyping, such as CAD models, analytical models, or physical models. This is because usually the selection is based on managers or experienced engineers. Is there any methods or criteria to help us make these decisions?
Yeah, so that's a great question. I really appreciate it. One paper that I've always loved is by Stefan Tomke, who wrote a paper on basically kind of error management during prototyping, right? And this is something that I practically tell my students and anyone that asks for prototyping advice. And you should be choosing your prototyping mode and your prototyping method based on first of all, what type of assumptions and what type of questions you need answers to, but also which mode or which method is going to give you the most errors. How are you going to find the most errors, right, while you're prototyping? And Stefan Tomke kind of came out with this idea that when you start to plateau, right, when you're finding all these errors with your prototype and then you start to plateau, that's a good flag that you need to switch modes, right? That you need to try a new prototyping method. You need to test your design in a different way. And I'll also take a quick moment to highlight the work from one of my best friends and awesome collaborators, Dr. Carly Loff. And Dr. Chris and I got to collaborate with her on this, but the prototyping canvas that we created is also a really quick and easy tool to use. It's very similar to the business model canvas to help you very rapidly select prototyping tools. And so at kind of a lesser granular level, right, that is also one way and one tool that can help with that. So.
Love it. Thank you, Jess. And a little shout out on Carly's work with Jess is that's published actually in ISED. The prototyping canvas is in the last ISED proceedings, or the one before that. It's actually the last one. So please take a look at that. Thank you, Jess. Vinayak, another question for you. This comes from Dave Rosen. Dave said you have fascinating ideas that you presented in your talk, and very much they were. And he goes on to ask, regarding Principle 3, what range of shapes can be used for higher order sites? And how do you know so you can guarantee the space, the filling property?
Excellent.
That space filling property. Yeah.
Thanks very much, Dr. Rosen, for the question. So, as long as we are considering solid geometry, right, you can go up to surfaces. Okay, so if you have any complex of shapes that is a combination of points, curves, and surfaces, in any combination, you can apply the principle. Now, having said that, making sure that it is space filling is actually in principle 1, because as long as you're doing Voronoi computation, by definition, you're making it space filling, right? So that aspect is sort of ingrained in the way the computation itself is happening. However, I would like to point out here that, and this is a discussion that I'm continuously having with Dr. Ackelman also, who's my collaborator in many of these projects, is that if you think about it, at least for linear geometries, say lines, we know that even in three-dimensional cases, what you're really going to get is analytic surfaces like paraboloids or hyperbolic paraboloids and so on. So it is possible for us to, at least for some cases, go beyond Voronoi computation and actually look at more analytic ways to produce the shapes if we know some of those rules, right? So, I guess that I hope that answered your question.
Great, Vinayak, thank you. You know what I actually hope you do is I hope you reach out to Dr. Rosen, and he does, of course, wonderful work in additive manufacturing at different scales,
Right.
and it'd be interesting to see if there's some nice applications of your work with his work as well. Devesh and Dan, we are at our time, so should we go ahead and wrap up at this point?
Yes, I think we can wrap up at this point. And
Great.
Thank you, Chris, for moderating it, and thank you, Jess and Vinayak, for a great talk. Just a reminder, as Dan mentioned, our next week theme is mechanics. So I look forward to seeing all of you on the next week for this. With that, we can stop recording, but rest, you can stay on the line if you want to interact with the speaker and have other questions.